Hi everybody, welcome back. Today we're going to talk about the geomorphic processes and landforms associated with the coastlines. So basically those involving waves and currents. So nice pictures here of different coastlines. We're going to try to explain the presence of some of these. So basically, as we're looking at coastal processes and coastal landforms, we'll break it down, or we'll break the discussion down into those of coastal erosion. So those occurring where the waves interact with coastlines. That involves beach erosion, erosion of headlands, and the formation of things like stacks and arches. We'll look at coastal transportation, where waves are going to be able to move sand offshore, deposit it in smaller waves onshore, and also wave actions moving along the shore, which we call longshore current, and the landforms associated with that. And finally, coastal deposition. We'll look at where the wave action is reduced, so the sand is now deposited to form beaches, sandspit, and things like tombolos. So you've all seen waves. That's a lot of energy that's being propagated by the wind, traveling across large stretches of ocean or sea, and finally releasing that energy in the form of waves along a coastline. The energy we can visualize in the form of circles that once they start to interact with the bottom of the substrate, that will deform that energy wave and turn it into an actual wave as we know it, breaking on the breaking on the beach surface, beach or headland, as we'll see in a minute. So the energy, again, breaking on a beach in this case, will transport some of the sand grains there and move them so that there's a swash both back and forward with an ebb and flow of the water. Now what we can see is that when we get larger waves and rough waters in the wintertime, we're going to get sand eroded from the swash zone and deposited just offshore. So that gives us a lot less sand on the nearshore beach environment. Let me get my cursor here so you can see it. So a lot of energy expended on the beach itself, removing the sand offshore. In the summertime, when we get smaller waves, calmer seas, we're going to see that same sand picked up from just offshore and deposited onto the beach, making a nice summer beach profile. We can see that in some images here. So a typical summer beach, nice and wide. The sand has been moved further inland. And in the winter, we have more erosion taking place because of the larger waves, and it's taking that sand and that's going to be shifted into a sandbank just offshore during the wintertime. We can see also that during the summertime, this sand is protecting the headlands and the cliffs, but in the wintertime, these cliffs and headlands can be more exposed to those larger waves. So here we see a late summer profile, Isla Vista, California, up by UCSB, with the cliffs of Isla Vista here. But if we look at the same scenario in December, we got a lot smaller beach, and we definitely see that some of these waves are starting to impact the cliffs. So we'll probably see some cliffside erosion here with some of the larger waves. So those cliffs, by the way, especially during the winter, we see wave action etching away at the base of the cliffs, and these cliffs will every now and then collapse. So we certainly don't want to build too close to those cliffs, even though that's very expensive real estate. At some point, especially with rising sea levels, that could be a losing proposition. You see here, this is one of the suburbs, the eastern suburbs of Sydney, Australia. Nice cliffs with bedrock exposures here, and very expensive real estate right on the edge of the cliff. But can you see that they're being undercut here? So those houses that are very close to the edge might not be there forever. and a little notch, and a notch will fall down. Now, in some environments, we see that we get cliffs forming with a wave cut platform, so a nice little flat area here. But then the whole thing gets uplifted due to earthquakes, let's say. So that's certainly the case in the West Coast, Southern California. We would get a wave cut platform with a cliff, and then the whole thing gets uplifted. So here's that old wave, there's that cliff, wave cut platform, and now a new cliff and a new wave cut platform being created. So in a coastline that has periodic earthquakes, we may see this happen, and we get a series of cliff and a bit of a wave cut platform has been uplifted to make a marine terrace in the same. There could be multiple versions of this. It could be 13, 14, 15 or more of these, and we see this sometimes in our coastline along the Southern California and Central California coast. I don't have a picture of it here, but Palos Verdes Peninsula has multiple terraces created, those former wave-cut platforms uplifted by earthquakes that occur every few hundred years or a few thousand years. Now, one thing to keep in mind here is that waves don't always expend their energy on cliffs or beaches. They can be focused on these headlands, and this is the portion right here. It probably has some resistant bedrock, and a lot of wave action will be, especially during the wintertime, during large storms, really directed towards expending the energy and eroding away that headland itself. And sometimes that creates some very unique landforms, including sea arches. We see that this would have been a headland that started to be eroded, and some of the weaker rock layers in there have been eroded to the point of collapse, creating these natural sea arches. Ultimately, this will probably collapse, and this would no longer be called an arch. In this case, we'd have a collapsed arch, and this would become a sea stack, being isolated there. You can see that in elements like this. So sea stacks are bedrock outcrops that are detached from the mainland. At some point, all of the rock material that used to connect the cliff headlands from these sea stacks, it's all been eroded, maybe into arches that collapsed, but ultimately that material has been removed. Can we see here that the waves are certainly acting on the base of this sea stack, and at some point that will get undercut so much that that sea stack would probably fall over during a large storm. Now, another thing about water movement, as the waves are breaking on the beach, they sort of move in this ebb and flow with a slight longitudinal movement. So the waves will go up and come off to the side. Next wave up and off to the side. And what that does is have a very slow movement of sediment, in this case from the left side of the diagram to the right side of the diagram. And that movement is referred to as longshore current. And we get sediment transported along beaches this way also. So sediment might be fed in from a river on the left side of the diagram and then moved back and forth in the swash zone along the beaches, but slowly, ever so slowly, moving from left to right along with this longshore current. What that can do, in this case of this diagram, the movement would have been from right to left. We get sand building up into a spit. So a sand spit will be the result of longshore current in this case here. So sand spits are very common features along coastlines. You've probably seen them quite regularly in multiple places. So they look like this. So the shallow areas of or let's say not very high elevation areas of sand built up primarily by this longshore current and the drift associated with it of the sediment. Sometimes the sediment would actually enable the connection of a headland to an island. So in this case, we have something called a tombolo. The tombolo is a sediment here, the sand sediment connecting the headland to an island. The island would actually be called a tide island in that case. And these are also quite common features these days along coastlines. Now, moving away from Southern California area, or let's say from the mid-latitudes towards the tropics, where we get water temperatures that are from the high 70s to the low 80s, that would be ideal conditions for the formation of tropical reefs. So tropical reefs are basically living organisms of algae and coral polyps that basically secrete a calcium carbonate shell, a exoskeleton, which build up into these massive arrangements that we would call reefs. We get them mainly in the tropics because that's where we get that warm water that is from the high 70s to the low 80s, ideal conditions. It can be much warmer than that. There are some tropical corals that will grow into temperatures approaching 100 degrees Fahrenheit, which is really, really hot, but that's not ideal, and that can't be for very long. That can only be for short periods of time. So around the low 80s would be probably the ideal temperature for reef development. And as the world is warming up through climate change, we're seeing that that's starting to have quite an impact on coral, not only because of the temperature, but also the acidification of ocean waters, because the calcium carbonate added to the water increases the carbonic acid component of water, decreases the pH, and that's not good for the development of coral reefs. So we're losing a lot of our reefs due to acidification as well as increased temperatures. Now, reefs fall into a number of categories. Here we have one called a barrier reef. So a barrier reef is separated from a mainland by quite some distance and also by deeper waters in the lagoon. So the lagoon is the area between the outer reef and the main land surface. If you've got deep water in here, we call that a barrier reef. But reefs come into three main varieties: barrier reefs, fringing reefs. Well, here we can see that we've got a reef around the edge or fringe of a land surface. Yes, it has a lagoon, but the lagoon is pretty shallow, on the order of feet. Most of the ones that I've done snorkeling and diving in across the world, usually just a few feet, maybe 10, 20 feet of depth would be pretty typical, but nothing is deep, nothing approaching the depth of a barrier reef where the lagoon could have waters that are very much on the order of maybe a couple 100 feet in some cases. And so here we're showing here a fringing reef along a mainland, a fringing reef around a volcanic island. And remember, when volcanic islands form, that's from tectonic processes that are maybe like forming an island as part of an island arc. But when the volcanism stops, the volcano and the rocks that are composing that volcano are cooling off, densifying, and also probably sinking. So as an island forms and then has less formation of lava, we see that the volcano, or the island made of the volcano, will start to sink. And as it does that, it actually form a ring. This would now be a barrier reef because it's now separated in deeper water because the island's been sinking. And ultimately that island, due to weathering, erosion, and that densification of the igneous materials, could get to the point where it actually goes below the water level. But the corals can keep growing on top of the older corals. So we actually get a ring of coral, but no island anymore. In that case, we will refer to that as an atoll or coral atoll. So the three major types would be barrier reefs, fringing reefs, and coral atolls. Beautiful atoll right here. They make for great diving locations or snorkeling locations. If you do get the chance to travel the world, especially in the South Pacific, there are some fantastic opportunities to go to places like Fiji, or Cook Islands, Samoa, Tonga. Just absolutely gorgeous places to go explore, beyond the typical places that people might come think of, like in the islands of French Polynesia, like Tahiti, Bora Bora, Moorea. Get out there, go see these places. They're absolutely gorgeous. They're wonderful, and go explore. That's all I can. That's probably my biggest suggestion and joy in life. Go explore to see what's out there. Thanks, everyone.